Alrighty, I think we are back. Running into some technical issues, but hopefully with a nice reboot of the old Computron, those are sorted out at this point. Alright, I think one of the great joys of this line of work is that you get to do the same thing over and over. What we left off with at the end of the last actual video that didn't have technical issues was how to enforce heap integrity at a single node, i.e., you have a heap with 3 nodes in it. How do you move these values around such that you end up with a valid heap? A valid heap, for our purposes, means having the largest value up at the top. These two don't matter as long as they are smaller than the top. That said, first of all, let's erase that. Haha. Let's go over what we have for our algorithms so far. I think I wrote them all out last time, and I think I might not do that this time. Let's just start with what we have. So we have L of I takes an index, and it gives us the index of its left child. That's what the L stands for. R of I, very similar, takes the index and gives us the right child. P of I takes an index, gives us the parent. And then, we never formally stated that these were some of our handy-dandy algorithms, but we do have left greater than node. And that is the one that is going to take our heap we're working with, our index we're looking at, and the endpoint of our heap, and it's going to tell us whether or not we want to swap the value of the node at our index with the value of its left child. We have a very similar function, much simpler, called RGN. Same thing, it's going to tell us if we want to swap the value of the node at our index with the value in that node's right child. And then I think the other one we need, and we will write this one out because I don't believe we actually did yet. We're going to want the last non-leaf node of our heap, and we don't actually need the heap or an index for this. This is just going to give us an index, and all we need is end. Now, remember how our array works. We've got 1, 2, 3, 4, 5, 6, 7 boxes. They are labeled 0, 1, 2, 3, 4, 5, and 6. There is nothing in box 7. That is not actually part of the array. So in this case, 7 would be our end value. So what we're going to do is take our end. We're going to subtract 1. Oh my. That's not going to work. Let's go ahead and erase that. We're going to take the parent of the last node in the array. The last node in the array is going to be our end value minus 1. You can think of end as an index, it's just not the index of an actual value in the array. So in this case, end minus 1 would be 6, and then we would look for the parent of 6, which, if you remember, is 6 minus 1 divided by 2. And if you remember your integer division, we're going to do something that is actually a bit more complicated, but for our purposes is just rounding down. So 5 divided by 2 rounding down is going to be... Why am I not convinced here? 0, 1, 2. Oh, okay. Sorry, I was getting our 7 node heap confused with the 10 node heap I use when we start coding. 4 and 5 and 6. So we subtract 1, we get 5. 5 divided by 2 is going to be 2. The parent of the last node, in this case, is going to be 2, and that is also going to be the last node that is not a leaf. The leaves are the ones on the bottom. All right, that will do it for recap, I think. Let's get into how to enforce heap integrity across the whole heap. Probably shouldn't have erased that handy-dandy picture of the heap, but that's okay. I'm starting to get a little better at redrawing it. Artistic skills would help here. I do not have them. If I were smart, I'd create like a PowerPoint deck or something. Okay, so if we want to... Oh, right. We'll just draw a slightly bigger heap here. Here's our 10 node heap. Let's make that clear that that is a left child. Okay, so what we want to do is we don't need to check any leaves because the algorithm we have for enforcing the heap integrity at a single node does not need to be run on leaves. It only needs to be run on non-leaf nodes. Hence, we are going to start with the last non-leaf. 1, 2, 3, 4, 5 in this case. 0, 1, 2, 3, 4. It's 4, right? Start with 0. Fence post errors, people. You will make them. I will make them. You will see me make them here. That's 4. That's 10. So, we are going to have nested for loops. And we are going to start here at the last non-leaf node, and we are going to enforce our heap integrity at every node starting at 4, going all the way back up to the top. Once we have done that once, we can ensure that the largest number in our heap is going to be at the root. We can't say anything else about the heap at this point. It may or may not be valid, so we're going to have to go through again and do it until we've ensured that the largest remaining value has been put into the root node of each subheap. For loop. So, what we're going to want to do is our outer for loop is going to run from 0 and we are going to want to always be less than or equal to the last non-leaf. Since we are using our 10 node heap, we'll just use 10 for end at this point. We'll just use the symbol end, I think is fine. So I needs to stay less than or equal to end. Oh, I'm sorry, it's not end, it's LNL. That thing we just went over. That wasn't what I wanted. How about a real erase? There we go. Last non-leaf, and that requires end. End is going to be 10 in this case that we're looking at here. And because we are going layer by layer here, we don't actually need to use the increment. What we are going to do is take the left child of I. So I is going to start at 0, and then it's going to be 1, and then it's going to be 3, and so on and so forth for bigger heaps. Alright, that's pretty simple. Now, we need to develop an inner loop that runs backwards. If you run it forwards, you end up with interesting problems. Interesting problems actually being the same problem. So, the problem we're going to run into here is that we're going to end up using unsigned integers. And if you have unsigned integers, the normal backwards loop that you would be tempted to use, something like this. Yeah, let's use j here. J equals end minus 1. J always be greater than or equal to 0. J minus minus. This would be the typical way you would run a for loop backwards. The problem is j will never be less than 0, because the moment j is less than 0, it overflows back to integer max, which is it's 2 to the 64th minus 1, I think. You pull out a calculator if you want to know what that is. The point is, that number is greater than 0, so this loop will run forever. So, we can't just run the loop backwards in the typical way. So we're going to... There's a couple ways you can solve this. The obvious one is you keep running it like this. This is sort of a generic version. Let's get rid of this and put in something more specific to our heap. Okay, so this would actually start at j equals ln l end. The end is not going to change, so it's going to start at end every time. And then the obvious way to do this is that j needs to be... Honestly, you could just say that... Oh, I'm sorry. Lost the plot for a second there. Okay, so j is going to want to be greater than or equal to I. But I is 0 in the first step of the outer loop. And then we run into that problem I was telling you about, the overflow problem. So, what we could do is we could put a little and in here. J needs to be less than something. What something could that be? Well, the obvious choice is just end. You could run into problems if you're using extremely large numbers, but this should work for most reasonably sized arrays. If you're working with big data, you'll end up with millions, billions of excuse me, indices. But for our computer science tutorial purposes, you're going to be working with less than 100, and that fits comfortably within the integer range of 0 to, what is it, like 400 billion? You know what? Let's take a moment and just look it up. Get our handy dandy calculator going. and 2 to the 64th. So looks like that's going to be about, is it 2 to the 64th? Do I have that right? 1, 2, 3, 4, 5, 6, 18 quintillion? Oh, big number. I guess it didn't really give us any enlightenment. Big waste of time there. And then, at this point, you can just run j minus minus normally. The other thing you can do is you can actually run this loop forwards, which is something I was experimenting with. It gets pretty crazy pretty fast because you need an inverse function where if you give it 0, you get lnl, and your inverse function would look something like this. inv, I forget what it actually needs. I think it's going to need an index and end, and then it's going to be, yeah, it's going to be lnl of end minus your index. And you put that in there, and that gets pretty crazy, but it does have the advantage of making the loop bounds look a lot easier. So in that case, if you were going to do it that way, your inner for loop would start with j equals 0. Oh, come on. Give me a real tittle. J equals 0, and you're going to run it out to j is less than or equal to lnl of end and you just subtract I from it. And then you have your usual j increment. I'm not sure which way is actually more efficient. This one strikes me as bad because you're doing 2 checks instead of 1 every time you loop, but if you end up doing this, you're using this every time you go through, and that's running a fair number of calculations on its own. This one, I think, is ultimately easier to debug, so maybe we should just go for that. Little logic change from what I was going to show you, but that's alright. You gots to be flexible. I think we can get rid of that now. Big old erase the board. There we go. Alright, so now the question is, what operation do you want to perform in the loop? Well, the operation is the operation of enforcing heap integrity at a single node, which we've already done. Hooray! Look at that. Oh wow, we are rolling right up on 20 minutes here. Okay. Let's get our logic filled in here, and then we'll break the video, and I think I'm going to roll right into the next one, because I have been wanting to get HeapSort out forever. If, how do you do that? If, and we have a function that tells us if we need to swap in both directions, and they were LGN, and LGN requires the heap. The index is going to be J, and then it needs the end as well. That'll just give us a boolean, so we can go right from there, and then we are going to swap. I can't remember if I went over this in any of the videos that are actually getting put up, but swap is going to be the same as it was in the bubble sort video. It is the XOR swap. If you're not familiar with it, oh, we need to end this. I'll go over it in the next video. We're going to go ahead and swap. It's going to be L of J. That would be the left child of J and J. That really is much simpler. Maybe that's why I kept bundling this. Then we've got an else if. This else if is what enables us to make that R of I function so simple. We would have to have more checks in it if we weren't doing that. Oh, come on. I am not very skilled at this in some ways. I noticed a lot of JavaScript people like having like a script font for their keywords. It does make it stand out. I guess I gotta give them that one. Else if, and then this is just going to be RGN, and that's going to be the same. Heap, index is J this time, and end. And then we will just swap R of J and J. Alright, we are over time, so I'm going to break the video here. Have an excellent day, and I hope you all learned something. Stay tuned for what looks like it's going to be part 3.